Hi, and welcome to the screencast. We're going to look at a special kind of graph called a parabola, and this is just an introduction to some parabolic graphs. So I'm going to read to you a situation. If you have a worksheet that looks like this, then you can fill this in with me, and if not, then just follow along and you can create the table and sketch the graph on a graph paper. So suppose the year was 2100, and a rare and precious metal had just been discovered on Mars. You and hundreds of other adventurers travel to the planet to stake your claim. You are allowed to claim any rectangular piece of land that can be surrounded by 20 meters of laser fencing. You want to arrange your fencing to enclose the maximum area possible. Now you might already have in your mind what that would be, what that might look like, what would be the maximum area possible, which is good. But if you don't, that's okay, because what we'll do is just kind of explore what those different things would be. So if in order for the perimeter to be 20, what would the side lengths have to be? So if I kind of start with something simple, like if this side was 1, then how long would this side have to be so that this would also be 1 over here? And then this one up here would be the same. So as I think about that, I think 1 plus something plus 1 plus something else equals 20. Well, halfway around would have to equal 10, right? If all the way around is 20, then from here to here must be 10. That means this would have to be 9. So if this was 9 meters, 9 plus 1 meter is 10, plus 9 is 19, plus 1 is 20. So that's one rectangle I can make, but there's others. In this space here, or on a piece of paper, sketch a couple other rectangles that would work, that you would be able to create with a perimeter of 20, and then we'll look at the different areas. So pause the video and go ahead and try that. So I have here a 1 by 9, or a 9 by 1. And I have 2 by 8, or 8 by 2, 3 by 7, 7 by 3, 4 by 6, or 6 by 4, depending on the way I look at it, and 5 by 5. So if I'm using whole number length sides, I've now found all the different possibilities. Now we're going to look at the different areas. So the area of a 1 by 9 would be 9. And then a 2 by 18 would be 16. 2 by 8, I'm sorry. 3 by 7 would be 21. 4 by 6 would be 24. And a 5 by 5 would be 25. Now if I was going in order, 1 by 9, 2 by 8, 3 by 7, 4 by 6, 5 by 5, the next thing I would say is after 5 comes 6. Well, 6 by 4 is 24. 7 by 3 is 21, 8 by 2 is 16, and 9 by 1 would be 9. But what about if we had a side length of 10? Well, if you had a side length of 10, the other side would have to be 0. So that really wouldn't make much of a rectangle, would it? So what we're going to do is we're going to create a table where we keep track of the length and then the width and the area. So we're going to start with the length of 0. So if we had a length of 0, then the width of that fencing would be 10. And we have 2 10s parallel to each other with nothing in between. So the area would be 0. So this one is actually not possible because you wouldn't have any area inside. So if we're going by whole number length sides, we go up by 1. Then that would be 1 by 9, and the area is 9. So complete a table going up by 1 meter each time for the length, and see how that affects the width, happens to the width, and then what happens to the area. I'm going to pause the video now and you try to complete the table. So you see I'm completing this table, and as the length in meters goes up by 1, the width goes down by 1. But you may notice that every time they add up to 10. 4 plus 6 is 10. 5 plus 5 is 10. 6 plus 4 is 10. 7 plus 3 is 10. So these are all whole number lengths, and here's all the areas. And then the areas start at 0 and then start increasing. 9, 16, 21, 24, 25. But then once you get to 25, notice the numbers start to decrease. And 8 by 2 would be 16. They're going to go down. So these numbers always add up to 10 because that's halfway around the shape. So that means that that's why they add up to 10, because the perimeter is 20 and half of 20 is 10. So if I was going to write the length as L, then what expression could I use for the width? So think about that. So for the width, I'm going to use 10 minus L. It's not L minus 10, it's 10 minus L, because if I did it the other way around and said I'm going to take the length minus 10, then I would have 1 minus 10 as negative 9 and 2 minus 10 as negative 8, but it needs to be positive. So I'm really subtracting the length from 10. That means the area would be the length times the width, which would give you this expression, L times 10 minus L in parentheses. So that's how you could use that to find any length and width. So if you instead did, let's say the length was 2.5 meters, then the width would have to be 7.5 meters. And you could still find an area. So they don't have to be whole number length sides. What we're going to do now, though, is we're going to graph the values in a graph. So here's the graph that I had started, and you can pause the video after I give you some descriptions. We're going to put the length on the x-axis, and we're going to put the area on the y-axis. And we're going to see what happens as I'm going to start with 0, 0, because if the length was 0, the area would be 0, and then 1, the length was 1, the area is 9. I'm going to go and I'm going to continue making a graph and seeing the shape of the graph. So go ahead and make that graph and pause the video. So here is the graph that it makes, and it kind of looks like a hill. This is called a parabola. And you may notice that as the length increases, first the area increases, but up to a point, and then after this point, then the area starts to decrease. And so the maximum point on this graph is 5, 25. There won't be any values in this relationship that are any greater, that have a greater y value than 25. So if I'm going to describe the domain and range for the situation, the domain, because we're talking about lengths, can't be negative, so the domain goes from 0 to the greatest length is 10. So x goes from 0 to 10. And the range, the y values, well, the lowest y value is 0, and the greatest y value is 25. So they go from 0 to 25. So that's your domain and range. And the rectangle with the greatest possible area is going to be a rectangle that's 5 by 5. So it's going to be a square that's 5 by 5. So if you have this packet, then this would be the second page in the packet, and you're going to do the example 6a. A rectangle has a perimeter now of 30 meters and a side length of L. Express the lengths of the other sides of the rectangle in terms of L. So that would mean if the length is L, then what would the width be? Well, if you could picture this, this is L, and then this will be the width. And when you add length plus width plus length plus width, you get 30. That means the 2L plus W have to add up to 15, right? So that's the width would have to be 15 minus L. So it's always going to be half the perimeter. So now write an equation for the area, and you can pause the video before you check your answer. So I can write the equation for the area in two ways. I can either write it as, since length times width is area, I can either write it in factored form, like this, or I can expand it and write it in expanded form. And this is the more standard form that you would see. I'm going to use that equation to make a graph. But before I make the graph, I'm going to actually answer this question D first. In question D, it says, what would the area of a rectangle be that had a length of 10 meters? So that's going to give me a coordinate pair. So what I did was I put 10 meters in my equation. You do that now and see what would the area be. I had 50 meters squared. So that means one coordinate pair would be 10, 50. I also know, though, if I would have used 5 meters instead, I would have 5 times 15 minus 5 is 10. So that actually is going to give me the same area. So they are going to be symmetrical. So 5, 50 and 10, 50. So now I have points that I can graph. I know the zeros here will be 0 and 15. We know that before from me solving equations. And I know I have these 2 points. Now I have 4 points. So now that I have these 4 points on the graph, I see that it looks like it's going to curve again. Now I'm going to use this scale in my graphing calculator. In the x-axis, I'm going to go from 0 to 15, and I'm going up by 2.5s. In the y-axis, I'm going to go from 0 to 60, and I'm going up by 5s. And if I hit graph, because I had typed here's the y equals, so I had typed that equation in earlier, and there's the graph. I'm going to push trace, and when I hit trace, it actually goes directly to that maximum point there, where x is 7.5. So 7.5, the middle of this graph, see how that's halfway between 5 and 10? 7.5 would be my maximum point at 56.25, and then it's going to curve back down. So I'm going to sketch that. So that means that the rectangle that with the greatest area, if I'm using 30 meters, would have a side length of 7.5. And if the length is 7.5, the width is 15 minus 7.5, which is also 7.5. So it's going to have a length of 7.5 and a width of 7.5, and it's going to be a square again. So a square will always give you the greatest area given a set perimeter. So if you have this worksheet and you have this packet, then you can finish number 5 on the back. If not, I will describe this to you so you can make a table. You notice in this table, the length is going up by 1. And then here are the different areas. So if you want to pause and copy those down, you can. I'll read this to you. The lifeguards at a beach are creating a rectangular boundary around a swimming area that can be used for water basketball. They have a fixed amount of rope to make the boundary. That's the fixed perimeter. They use a table to look at all the different possible arrangements. So what patterns do you observe? And I'm sure you have some. What is the fixed perimeter they were starting with? Well, you can pause the video now and figure out what the fixed perimeter would be and write some expressions for what the length and width would be. So go ahead and pause the video now and do that. So here is the answer then for the fixed perimeter would be 32 and the side lengths. And you should make a graph of that because you have the table, so use the table to help make the graph. But I really want to talk to you about part D. So in part D, I took the length L times the width, which is 16 minus L, and I multiplied them out. And I wrote this in standard form. So I have negative L squared plus 16L. And we're going to see when the area is 11.5 square meters. So I'm going to use the graphing calculator for that. So what I did in my y equals, I typed in the equation for area, and then I typed in where y equals, the other equation is y equals 11.5. So then when I hit the graph, you'll see this straight line here. This is where y is 11.5, and it intersects the parabola right there. So I'm going to find the intersection point by doing second trace 5. And it's going to say the first curve, and the first curve is the parabola. The second curve is the line we just created. I'm going to hit enter again. Here's my guess, whatever. And my answer is it intersects. So when x is about 3/4, then y is 11.5. So that means if the length is about 3/4, the width would be about 15.25, and that would get you an area that's very close to 11.5. All right, so I just wanted to show you that last part. Thanks for watching. Have a great day.